So we talked about redistribution in the last section, and now we're going to talk about the volume of distribution, and we're going to talk about protein binding of drugs in this section. The volume of distribution is a concept. It is a useful concept thinking of an animal that might have a particular condition. It is the idea that basically you're looking at the animal's body as a vat of liquid, and and the main idea that we use with this concept is that the concentration of the drug in the blood is the same as the concentration in the body tissues. This is not a completely accurate idea, however. I've talked about how there can be active transport pumps that bring drugs into different tissues at higher concentrations than are in the blood. I've talked about how our P glycoproteins can kind of be a refusal mechanism of certain tissues to decrease the amount of that drug in that particular tissue. And I've also talked about the concept of perfusion of a tissue that would make it have a higher or lower concentration of a drug. So this is not entirely accurate, but it's useful for certain situations to think about this concept. The basic idea is that if we have a high volume of distribution, that's going to be a very large amount of fluid in the body. We have more tissues that are penetrated, but that also means that the concentration of the drug is going to be lower because it's more dilute. So a useful way to think of this is if we have these two different vats, if you will. So this would be a body of an animal that has less fluid in their body, and this would be one that has more fluid in their body than normal, okay? So the concept is really thinking about the normal amount in the animal's body. And you might be able to think of some situations that would result in these conditions, and we'll kind of go over those. But the concept is if we have a small volume of distribution, a small amount of water in the animal's body, and we add 100 milligrams of salt, you can see that this is very concentrated. These molecules are close together. On the other hand, if the animal has a lot of fluid in the body and we add the same amount of salt, that concentration is going to be lower. These molecules are more spread out. So the blood volume concentration would be lower in this animal than this animal. So looking at what are we talking about in terms of real animals and real conditions, this is a dog that has ascites. Ascites is a condition where we have extra fluid in the abdomen. This condition results from one example is a heart condition where the heart is not working very well, and especially a right-sided heart condition where the blood is not being pumped very well out of the right atrium and ventricle into the rest of the heart. The blood will begin to back up, and it backs up to the organs in the abdomen. Also cranially, it will back up. You'll see a jugular pulse typically in animals that have this condition. But in the lower abdomen and the caudal vena cava, that blood will back up and it will congest the organs that are downstream, the liver, the spleen, and fluid will actually begin to come out of those blood vessels and organs into the abdomen. And fluid will accumulate in the abdomen, and that is what is ascites. So this would be an animal that would have a larger than normal volume of distribution. We have a lot of extra fluid just accumulating in the animal's body. So in that situation, if we gave a normal dosage, this animal would have a lesser plasma concentration of a drug. So in order to compensate for that, we'd want to give more drug. So more drug per weight of animal. On the other hand, if we have a small volume of distribution, it's going to be the opposite. So this is a kitty cat. We've tinted the skin of this cat to look at its hydration status. And yes, it's a still picture, so you're seeing the skin tent just staying in place. But if you were there, you would see that that skin tent would stay there for longer than normal. So this cat is dehydrated. And if we were to give a normal dosage to this cat that has a smaller volume of distribution, that dosage would end up, we'd have a plasma concentration that would be higher than probably what we want it to be. So we would go on the low end of a dosage range if we are given a range, or we might just decrease it more from the normal dosage area. So that's how we compensate for a large and a small volume of distribution. So that concept is useful for these particular conditions, but remember that certain areas of the body may accumulate or may have less drug. So so they're compartments. We can view those as compartments that would not follow this particular concept. All right, so also drugs combine with proteins. Now, the drug manufacturers take this into consideration. They look at the drug and they consider whether the drug is what we call highly protein bound. When a drug is highly protein bound, if we were to take a sample of the plasma from the animal, it would look like we have a high concentration if we're measuring both the bound and unbound drug. The drug that is unbound is the drug that is active in the body. The drug that is combined with a protein in the bloodstream is going to stay there and it's not going to have activity. Drugs can also become protein bound in tissues once they get into the tissues. So they can seem to have a longer effect because they stay there. What happens is that there's a certain percentage of the drug that is protein bound and is not protein bound. And as the drug leaves the bloodstream, some of that protein bound drug will become released from the protein to keep that particular percentage that is protein bound and not protein bound. So eventually the drug will leave the bloodstream even if it is highly protein bound. But only the drug that's free is going to be the one that will act and be distributed to tissues. So the measurement of the protein bound concentration, if it's bound and unbound that we're measuring, is going to look like more than what we might have in the tissues and more that might be active in the animal. So hang on, I'm going to go back up. I didn't mean to go back. I'm going to go back to this slide. So we need to think about conditions and look at our patient. If our patient does not have as much protein in the blood, and you all are probably just starting to look at blood in your clinical pathology class, and you take a blood sample, you spin it down, and you measure the total protein and the hematocrit, the amount of red blood cells. So that simple measurement of total protein, if it is low, we have to realize that there will not be as much drug bound to proteins because there's not as much protein there. And we'll have to adjust the drug concentration for that. And the direction we would do that in is we would decrease it because there's not as much protein to bind with a particular drug. So we don't worry as much about a high protein status. We don't seem to have that quite as much as a low protein status. A high protein status, if you think about what might lead to that particular increase in total protein, one of the things, and you guys are going to be talking about this, but one of the things that would lead to a high total protein value is dehydration. So simply hydrating the animal might get it back into the normal total protein in the blood, and then giving a drug, we won't have to worry about adjusting the concentration.